So 5.4 is the fundamental theorem of calculus. So part 1 says that if f is continuous on a to b, then the function f of x is equal to the integral from a to x of f of t d of t. It has a derivative at every point x in the interval a to b, and the derivative equals the derivative of the integral from a to x of f of t d of t equals f of x. The proof states that the definition of the derivative directly to the function f is the limit of, as h goes to 0, of x of x plus h, equals f of x over h. If we plug it in what f of x plus h equals an f of x, we get the limit of the limit as h goes to 0 of the integral from a to x plus h of f of t d of t minus the integral from a to x of f of t d of t all over h. This reduces down to the limit as h goes to 0 of the integral from x to x plus h f of t d of t all over h. We know from the mean value theorem for definite integrals that f being continuous takes on its average value at least once in the interval. So the limit as h goes to 0 of 1 over h times the integral from x to x plus h f of t d of t will equal, at some point, f of c, or some c between x and x plus h. So by knowing this, the derivative of f of x is going to be the derivative of the integral from a to x of f of t d of t, and this will equal f of x. So example problem on page 295 is we're supposed to find the derivative of the integral from negative pi to x of cosine of t d of t. So what you do is you just plug in x where the t is, because you're taking the derivative of the integral, and your answer becomes cosine of x. There is also the chain rule when it comes to taking the derivative of an integral. This happens when we want to take the derivative of the integral from 1 to x squared cosine of t d of t. You can use substitution by setting y equals to the integral from 1 to u of cosine of t d of t, and setting u equal to x squared. The chain rule states that the derivative of y with respect to x is going to equal the derivative of y with respect to u times the derivative of u. An example of this would be the derivative of the integral from 1 to u of cosine of t d of t multiplied by du. So when you take the derivative of the integral, you end up with cosine of u multiplied by du. And that, when you plug back in u, you get cosine of x squared times 2x, because 2x is the derivative of x squared. Then you simplify it down, the answer is 2x cosine of x squared. Another problem is when the variable is on the lower limit. So an example of this is y equals the integral from x to 5 of 3t sine t of t. And what you do here is you make it negative so that the limit will switch. So it would equal negative integral from 5 to x, 3 of t sin of t d of t. And then you can plug in your x, and it would equal negative 3x sine of x. The second part of the fundamental theorem of calculus states that if f is continuous at every point of the integral a to b, and if any derivative of f are at the integral at a to b, then the integral from a to b of f of x d of x is equal to f of b minus f of a. This is also called the integral evaluation theorem. So an example of this is on page 300, example 5. They want you to evaluate the integral from negative 1 to 3 of x to the third plus 1 d of x. When you take the integral of this, you get x to the fourth over 4 plus x. And then you're going to take that from negative 1 to 3 because those are your limits. When you plug in 3, you get 81 over 4 plus 3. And then when you plug in negative 1, you get 1/4 minus 1. When you simplify this down, it's going to equal 24.